Welcome! This is my second video about understanding space weather. This video is going to cover the source of the sun's energy. I'm writing a series of 5 papers for the Bulletins of the American Meteorological Society about space weather. 3 of those have been published or are about to be published. And these videos are to explain some of the points made in those papers and to help understanding some of the scientific terms used in studies of space weather. So what does the sun actually emit that can affect the Earth? Well, the primary emission is radiation, that is light, and it emits that radiation across the entire electromagnetic spectrum from gamma rays to radio wavelengths. It also emits particles in the form of the solar wind, coronal mass ejections, and neutrinos. And there's also another component called the magnetic field that stretches out to the very edge of the solar system. Most of the energy emitted by the sun is in the form of radiation. The sun produces about 4 times 10 to the 26 joules per second in the form of radiation, light in other words. The Earth gets about 2 times 10 to the 22 joules of that each day, or about the same amount of energy as is in all of the coal reserves on the planet, and more than is available in our natural gas and oil reserves combined. If we could just capture 0.006% of that sunlight, all of our energy needs would be fulfilled, and we would not have to burn any more fossil fuels, ever. Well, where does the sun get all of its energy from? There have been many theories put forward over the years. One of the initial ones that it was a chemical reaction like the burning of coal, but that would give the life of the sun to be very, very short indeed. The second one was that gravitational collapse was causing the sun to warm up and produce all this energy. However, that too produces a sun with a very short lifetime, and besides which we've not been able to measure any significant change in the size of the sun. The only one that fits is that there's a nuclear fusion reactor going on in the center of the sun, and that relies on Einstein's very, very famous equation E equals mc squared, which basically says you can get a lot of energy from destroying a very little mass. So how much mass does the sun lose to produce all this energy? It turns out to be about 4 million metric tons every second, and I've done a little calculation at the bottom of the screen here to show you how to get to the 4 times 10 to the 26 joules using those numbers. A very important quantity in considering all of this is the total solar irradiance, or the energy reaching the Earth. Total solar radiance is relatively stable at about 1366 watts per meter squared. However, the passage of large sunspots across the sun can dim that value for a few days, but no more. Total solar radiance also varies with the solar cycle by about 0.1%. So there's very small variation in this. In fact, effectively, the sun's energy input is a constant. These small changes have very little effect on Earth's temperature, for example. Are there factors that can enhance the total solar irradiance? Look, for example, what about flares? Flares are large explosions on the sun, and we just had the 8th largest flare on record just a few days ago. So did that affect the total solar irradiance? If the sun is producing about 4 times 10 to the 26 joules per second, how much energy does a typical flare produce? Well, a large flare produces about 10 to the 26 joules. So it's sort of an equivalent amount of energy. However, a flare can last quite a long time. The X flare that we're talking about here lasted for about 6 hours. So if you take the time of the flare and divide it into the amount of energy that the flare has produced, you get a typical increase in total solar radiance of much less than 0.1%, which is hardly detectable. In fact, we've seen very few flares produce an effect in the total solar irradiance to date. One question I'm often asked when talking about this subject is, will the sun run out of mass if it's losing 4 million tons every second? Well, we can do a quick calculation on that. If it's using 4 billion kilograms up every second, and there's 32 million seconds in a year, and the remaining life of the sun is supposed to be 4.5 billion years, we can multiply all these together and work out how much the total mass loss of the sun is. And that turns out to be 600 trillion kilograms. But the mass of the Sun is 2 times 10 to the 30 kilograms, and so this amount over the lifetime of the Sun represents 0.03% of the mass of the Sun, and so we have no real fear that the Sun is going to run out of mass due to its nuclear fusion process. So how does the Sun create all of this energy? Well, first of all, we have to look at the composition of the Sun, which is made up primarily of hydrogen and helium. Now, because the temperatures inside the Sun are so high, the electrons are stripped off of the hydrogen and helium atoms, and so we basically have a plasma made up of hydrogen nuclei, i.e. protons, helium nuclei, and electrons. So this is a fluid, a charged fluid. Inside the Sun, in the core of the Sun, the temperature is very high. It's about 16 million degrees Kelvin. It is also very dense in the core of the Sun because of the weight of the overlaying layers of the Sun, and its density is estimated to be about 150 tons per cubic meter. Now that compares with gold, which is just under 20 tons per cubic meter. So the density in the core of the Sun is nearly 8 times more dense than gold. And remember, this is still a fluid, so some very strange things are going to happen under those circumstances of high temperatures and high densities, and one of them is nuclear fusion. Well, how does nuclear fusion work? Well, first of all, you take 2 protons and you make them collide, and that's going to happen quite often under these circumstances of very high pressures and very high temperatures. When that happens, you produce a deuterium nucleus, which is a proton plus a neutron. In the process, a positron, a positively charged electron, is emitted, and a neutrino. The next step is when you collide a deuterium nucleus with a proton, and that produces a helium-3 nucleus. That is 2 protons and a neutron. In the process of doing this, a gamma ray is emitted, which is part of the energy that we see eventually emitted from the surface of the Sun. In the last stage of this process, we have 2 helium-3 nuclei collide. They produce a helium-4 nucleus and emit 2 protons. So throughout this process, we've had the emission of a positron, a neutrino, a gamma ray. So we've been producing energy all the way through this process. What happens when the core of the Sun runs out of its hydrogen fuel? Well, that won't happen for about 4.5 billion years. But when it does, it will start to burn helium, and the very nature and structure of the Sun will change. It will become a red giant. It will certainly engulf Mercury, probably Venus too, and may even extend beyond the Earth's orbit. I hate to end on such a downer as that, so I do have a piece of good news. Some time ago, we eventually got the power company to agree to all the paperwork, a solar panel system, and also put in a meter to monitor how much energy we produce. As I've been typing this, our solar panels finished producing their first megawatt hour of energy. Now, as we don't use anything like that amount of energy ourselves, much of that has gone into the grid, and so therefore some of the electrons you are using to view this video may well have come from us. You are very welcome. Until next time, goodbye.